Yeah, let's take a look at where we left off, and today what we'll do is finish 6.2. And nobody emailed me for an extension, so everybody probably got that. But I'll do another example of that, the last type of integration by parts where you do it twice and then move the integral over. And then we'll move on to, the other sections in the 6. Okay. That's what I'm looking for. So last time we had reversed the product rule, integrated by parts. And we looked at polynomial multiplied by a trig, or polynomial times exponential, and then a polynomial multiplied by a logarithm. We used natural log every time we did that, but you could use log base, whatever, if you want. And then the last one, we did one example of the exponential multiplied by a trig function. So we're gonna do one more example of that. So this one was the one we had done. Oh. Let's do one more like that just to remind us of how to do it. So let's take and integrate cosine of x times e to the 5x with respect to x. Now remember, on all of these, the key thing is which part do we call our f prime, which part do we call our g? Okay. On the previous example, where we did sine of 4x and then e to the 2x, remember which one we called our f prime, which one we called our g? They have that in their notes.
F prime was e to 2x.
F prime was e to the 2x on that one. G was sine of 4x. That's good. Now, that time we did the g was our trig function. Okay. It doesn't have to be if we don't want it to be. If we want to have our g be our exponential function, it'll work out as well. And our letter f prime be our trig part, that's fine too. Does that make sense? So whichever way you'd like to do that is fine. Since I had forgotten which one we called which last time. So since we used f prime as the exponential last time, this time I'll use f prime as the trig and g as the exponential. Okay. Again, you could have done it the opposite way if you'd like. Whenever we do that, we have to figure out what f is and then what g prime is. Remember, when you go from f prime to f, we integrate. So integration of cosine is a positive sign. When we go to g prime, we take a derivative. So that's 5e to the 5x. So we're saying that this integration is equal to f times g, that's sine times e to the 5x, f times g, minus integrate f times g prime. Now your f times g prime is going to be 5 sine x e to the 5x. And we're going to integrate that with respect to x. So we do another integration by parts on this one. Before I do though, I'm going to distribute that negative sign. Just to make, so I don't have to distribute it into multiple terms later. And on this one, it is a little bit tricky in the sense that not awful, but I like to when I integrate by parts, when I'm dealing with this option, I like to once again do the f prime as the trig component, just because we did it over here. And I'll do the g as the exponential component. And if you want to attach that 5 to the g, you know, that coefficient of 5, doesn't matter which way it goes. I'll just use that for now. So f in this one, if we integrate sine, you get negative cosine. So we end up with a positive 5 cosine of x. Negative, negative, get the positives. And then when you take a derivative of g, once again, you get 5e to the 5x. So we have cosine x, e to the 5x dx. When we integrate, we have this part, our original f times g, plus now this integration becomes our new f times our new g. Minus integrate our new f times our g prime, our new g prime. That's going to be 25 cosine of x e to the 5x integrated with respect to x when I do all that. Because I end up with the same integration other than this coefficient, what I can do is I can think of this. You don't have to write this down if you can see it. I'm just saying, you can think of it as 25 minus 25 times that same integration. So because after 2 integration by parts, I get the same integration, although with a different coefficient. Now I can add 25 times that integral to both sides. Again, this one was kind of nice. Sometimes you end up with ugly fractions in front. In fact, if I would have swapped which one I called the G and which one I called the F prime first, then we would have been dividing by 5, right? Instead of multiplying by 5. When you integrate, you divide by the 5. When you take a derivative, you multiply by 5. So we would have ended up with uglier fractions, but same thing. Now, again, I stated this last time. This next line that I'm gonna write is gonna be almost true. There is a plus constant that you have to worry about by doing this. These integrations could be different by a constant. All right, so when we do that trick, we have to be conscious that when I have this step, this 26 times the integral equaling sine x e to the 5x plus 5 cosine x e to the 5x. There is a plus c over here that I'm not necessarily including right now. So there is a plus c. I'm not going to write it till the very end, but it exists over there. And then what I like to do is, because oftentimes you end up with ugly fractions up here, I just get used to multiplying by the reciprocal on both sides rather than dividing by 26 on both sides. So when I write this, I'll just write, let's multiply by 1 over 26 on the left-hand side, multiply by 1 over 26 on the right-hand side. And then we'll do a plus c at the end too, might as well, just to make sense of it. That cancels out my coefficient, and I end up with my final answer, which says cosine of x e to the 5x is equal to, and if you want to distribute, you can. If you want to leave the brackets, you can. I think I'm going to distribute, just I've done that. But again, if you write your answer with brackets, Moodle should tell you you've done it correctly. As long as it's written correctly. So there it is. 2 integration by parts. You end up with the same integration on both sides. And so you do this trick where you add, or you could possibly subtract, but in this case, we added 25 times that integration to both sides. Now, there are some things you could do as well with integration by parts that are actually easier using other methods. So I didn't go over this one, but if you wanted to try to use that same trick with sine times cosine, you could. However, sine times cosine is actually easier to do with substitution. You let your sine be your u, your cosine now is your cosine x dx is now your du. And you can do that other way. So when choosing whether to do integration by parts or substitution, usually if you have the option of doing either, you choose substitution. It's a little bit easier, usually. Okay. The other thing I'll mention is that when you have definite integrals, you can also use integration by parts. I'm not doing that right now, but you can use integration by parts. Then after you're done with that, evaluate when you plug in 1, evaluate when you plug in 2. We've also seen how to do these definite integrals using our calculators. And so we can apply that as well. All right. Okay. The rest, so we've done substitution, which is reverse of the chain rule. We've done integration by parts, which is a reverse of the product rule. These are obviously not the only ways to use substitution. There's other ways to do integration by parts as well, other scenarios that would fit. All right. But for the rest of chapter 6, we're just going to keep adding on to our techniques of how to integrate. Okay. We're going to take some other techniques and utilize those to help us integrate. So the first newer technique is trig integration. So this is integrating with trig functions. And it's basically fancy substitution. Okay? In fact, both 6.3 and 6.4 are going to be fancy substitution in different ways. Okay? We're going to substitute out our trig functions, but then we're also going to throw in what we know about trig identities. So it's essentially substitution where u is a trig function. And then we can also utilize our trig identities. Okay. So anytime we're using substitution, we need to make sure we get the du, dx exchange right. And it's not always a du equals dx. It's going to be a du is equal to some sort of trig thing times dx. Okay. So like I said, the big idea is substitution with trig identities. The biggest trig identity is going to be that top one. Cosine squared plus sine squared equals 1. Sometimes that's called the unit circle identity or Pythagorean identity for trig functions. There's also identities for sine squared and cosine squared using double angle formulas. Cosine squared is 1/2 times 1 plus cosine of double whatever that angle is, 2x. And then sine squared is very similar to that, 1/2 times 1 minus cosine of 2x. That top trig identity That is the big one. That's the one we use a lot and the vast majority of times. Okay. So let's take a look at how to integrate using substitution a couple of these problems. We have sine x times cosine to the fifth dx. And then we have sine to the third times cosine squared. That one down to put over here. All right. So like I said, it's just fancy substitution. So anytime we're dealing with substitution, we have to pick the right inside function. Now, in this problem, it's fairly straightforward what we want to pick. Okay? We pick it in a very similar way that we picked it in 6.1. We say, what's the inside function? Well, an inside function here, you can think of as cosine, because it's being raised to the fifth power, where sine is only being raised to the first power, right? That makes sense? In this case. And so your intuition on this problem is probably right. Okay. So let's go ahead and do that. U is equal to cosine. That means when you take a derivative of u with respect to x, well, derivative of cosine is negative sine. So my du dx exchange is this, or I could also write it like this, either one I can use. Since I already have a positive sign, I'll probably use this one. And so I'll do a rewrite. Cosine to the fifth times sine x dx. This cosine of x is just u, so now I substitute. That's u to the fifth, cosine to the fifth, it's u to the fifth. And then sine x dx gets exchanged for a negative du. I'll put the negative in front of my u to the fifth. You could also put it in front of the integration. Now, this is just variable to a power integration. So we can integrate and get a negative 1/6 u to the sixth plus any constant. And now we can back substitute u was a cosine. So that is -1/6 cosine to the 6th plus c.
I have a question.
Yeah,
When you did the DU, how did you get the negative sign to the? How did you get it to become negative?
I just took a derivative of cosine, and the derivative of cosine is negative sign.
Okay,
So when you take a derivative of cosine, it's negative sign. When you integrate cosine, it's positive sign.
okay, so how at the end part, how did you get the negative sign?
Oh, that's just multiplying both sides by -1 or dividing both sides by -1.
Oh,
Yep. So I can exchange the sign by multiplying both sides by -1 or dividing both sides by -1. So, yeah. So there you go. So this problem works just how it would have worked in 6.1. Okay? And there's very little here that's new that we couldn't have done in 6.1. All right? The issue is what happens when we get into exponents where you don't have just a sine to the first, where we have like a sine to the third and a cosine squared. In one sense, if we looked at this while we were trying to do 6.1, we'd say, what's the inside function? And you say, gosh, they both look like inside functions a little bit because they're both raised to higher powers.
what is 2 close?
Yeah, why though?
I mean, it's in the middle. That's like, whenever I think about like the inside function, just think about which one's in the middle of it.
Oh, okay, location.
Yeah.
So if you did cosine squared times sine to the third dx, would you pick sine? Like if you just flip the order?
Yeah,
Okay,
but is it?
so it's not that easy.
Okay.
It is cosine, but it's not because of that.
Okay.
We are gonna use cosine because I know how it's gonna work out in the future, all right? So we gotta put our future glasses on.
So to be honest, we could use either one then.
No, in this case, it actually has to be cosine.
Okay.
So here's what we do. We put our future glasses on. And I say, when I take a derivative of cosine or sine, I'm gonna get either plus or minus the other one. Right? Depending on which I use. So that's gonna use one of the cosines or the sines along with the dx. Okay. And it turns out I want an even one remaining. This is gonna be really weird sounding until we get this, because remember that cosine squared plus sine squared equals 1 identity? Well, that only uses sine squared or cosine squared, which means I can use even powers in my exchanges between sines and cosines. So the short of the story is I'm going to use cosine of x as my exchange because it has an even power. So it's a long way to say, I want to use cosine since it has an even power. Okay? And in particular, maybe even more important, the sine has an odd power. That's probably the more important reason. Okay, I'll write that down too. And sine x is odd power. And if you look at the one we previously did, that sine of x was only raised to the first degree. That was an odd power on sine of x. See that? And usually I look at the odd powers. If there's a choice between two different odd powers and we're dealing with sines and cosines, then I choose the smaller of them. Okay. So that's a long way of saying, in this case, we want to let u be cosine and it magically works out all the numbers. Okay, all the exchanges.
You said if they're both, you wanna use the smaller one, right?
I'd use the smaller one if both are their odds.
This-
No, smaller one, I'm sorry. When I say smaller one, let me rephrase that. I'll use the larger one for the u, the smaller one for the d.
Okay,
I'm sorry.
you're fine.
Yeah, when I say use, we have two uses, one of them. I think I'm going to. Yeah. So yeah, one of them is gonna be used for a u, and the other is gonna be used for the du exchange. If I have a choice and they're both odd powers, then the larger of the odd powers, I'm gonna make my u. And the smaller of the odd powers is gonna be absorbed in the du dx exchange. Just to make my life easier. You can actually technically use both. But if one is an even power and the other is odd, then the even power becomes your u. The odd is gonna be in the. Now this is for, this rule here is for sines and cosines. If you're dealing with other trig functions, it works a little bit different. All right, so this rule, just for sines and cosines, other trig functions will work a little bit different. Now, the other thing I'm gonna do right now, right below this, is use my space here to just rewrite my standard trig substitution, which is sine squared plus cosine squared equals 1. I'll leave a space right there because I'll write another line in just a second. So here's what I do. I want to rewrite cosine squared can be a u squared. Sine is going to get matched up with the dx for this exchange. So I'll do my first rewrite. And I'll pull a sine x over with this dx for the du exchange. All right. Like I said, the cosine squared, we can now make a u squared. And here's where this trig identity comes in. Now we do another rewrite step. And we say, well, sine squared if I solve for that by subtracting cosine squared from both sides, it gives me 1 minus cosine squared. And because I can exchange out cosines for u, I'd rather be dealing with cosine squared, or 1 minus cosine squared, than dealing with sine squared. So I'm gonna replace the sine squared with a 1 minus cosine squared. And because I know I'm gonna exchange that sine x dx, I'm just gonna leave the sine x dx alone. Now we can substitute. That gives me 1 minus u squared multiplied times u squared times a negative du. I don't want to write that. I'll put the negative up here. Up front. When I have a negative du, I usually just put the negative on the outside. Or at least in front of the. Here. Now let me rewrite that, because we're gonna integrate this. This is hard to integrate as it sits, but if you multiply the u squared times 1, u squared times u squared, and then you distribute the negative, what you're gonna end up with, -1 times u squared is negative u squared. Negative times negative u squared times u squared is a positive u to the 4th. And this is a really easy polynomial to integrate. See that? I just multiplied the u squared. Now we integrate -1/3 u to the 3rd plus 1/5 u to the 5th plus c. And then the last step is our back substitution. -1/3 u was cosine, so that's cosine of x to the 3rd. By the way, books and when I write it on the board, I write it like that. But in Moodle, it's gonna want that exponent on the outside. And then when you actually write it in Moodle, it'll automatically exchange it into the inside. Does that make sense? So when you write it in Moodle, if you're writing cosine to the 3rd, you write cosine parentheses x and then caret 3. And then Moodle will make it look like that. But if you put the caret like in here, it doesn't recognize the Moodle, so. And that's it. That's the whole thing. So it's this weird even odd thing, and I don't like to write a ton of rules as far as, oh, when sine is even and cosine is odd, do this, or cosine is even and sine is odd, do this. I just like to say, you kind of look ahead into the future, and you know you're gonna have to peel one of these off and attach it to the dx for that dx du exchange. All right, you know that's gonna happen. And then you hope that the remaining part is even. Whatever you peeled off. So if I peeled off a sine and attached it to the dx, the remaining sine is to an even power. If I would have pulled off a cosine and attached it to the dx, the remaining cosine would have been to the first power, and I would not have been able to use this trig identity anymore. So I'd have had an extra cosine lying around that I can't deal with. That makes sense? And as always, when in doubt, if you don't see that right away, just pick one. See if it works out. If it doesn't work out, restart, pick the other one, right? There's basically two options here. You pick the u to be sine or the u to be cosine, and hope one of them works out. All right. So let's do this one. Actually, I'll let you do this one. But let me get you started. So in this case, both are odd powers. So if you pull off the sine and attach it with the dx, that's going to be okay to do. You'll have an even sine left. If you pull off the cosine and attach it to the dx, that'll be okay to do as well, because you'll have an even cosine left over after you attach one cosine to the dx. That makes sense? And so when you have this as either is okay, what I tend to do, if either is okay, like I said earlier, is let your u be the higher exponent, if either is okay. So let your u in this case be sine, and then you'll have a little bit easier of a time with your trig substitution. I'll do the other way too. I'll show you what would have happened on the other way. But I want you to try this, letting your u be sine. All right, so let me go through this one. So like I said, in this case, the easier version is to let u be sine. Okay? And if you do that, then our du dx exchange is du is equal to cosine x dx. So I'll peel off one of those cosines. And attach it to the dx for that exchange. That'll exchange for my du. Now I have sine to the 7th. I have my cosine x dx, and now I got to get rid of this cosine squared. Since that's an even power, I can do that utilizing this identity, this unit circle identity, Pythagorean identity, however you'd like to say that. Cosine squared can be exchanged for a 1 minus sine squared of the same argument obviously. That's just subtracting sine squared from both sides. So I'll do that exchange. And now everything is in terms of sine except for my du dx exchange, which is what I want. So now I substitute that gives me a u to the 7th times 1 minus u squared times du. I will multiply that u to the 7th through. Almost always, if you use the trig identity here, there's going to be some multiplication here before we can integrate. So we get u to the 7th minus u to the 9th integrated with respect to u. That's 1/8 u to the 8th minus 1/10 u to the 10th plus any constant that we want. And now we can back substitute. U in this case was sine, so 1/8 sine to the 8th power minus 1/10 sine to the 10th power plus c. Yeah,
Would I be wrong in saying that there's a pattern when you use sine and cosine? Like to the final answer, because the last one was sine 3x times cos 2x, and it finished with 1/3 cos 3x to 1/5 cos 3 or 5x, so you're just adding the two exponents for the second one. We did the same thing here.
That is the case. It's a little, so in both of the last two cases we did, the U had been raised to a power, but in each case, the other part was to the third power. So I don't want to be too broad in the pattern. The pattern exists because in both cases, they were raised to the third power. And so we essentially had to multiply by U squared or 1 minus U
Right.
squared in here. But you're right, if this were signed to the 93rd, it would look the same, except this would end up as a U to the 93rd.
Okay.
And so you'd end up with that same kind of pattern. But I don't want to get too broad, because if you go cosine to the 5th, then that pattern will break down.
Okay.
Any questions about this? Now, like I said, this was actually the easier way to do this. It is possible in this case, because they're both odd powers, it is possible to let your U be cosine as well. It's just a little more difficult. So don't write this one down. I'm going to show you this, but it's a little bit more difficult. Just follow along. If you want to write it down, that's fine, but I'm going to go through it very quickly. All right. So I'm going to do the same one, but I'm going to let U be cosine of X. And that means we have that negative du is equal to sine x dx. I did 2 steps there. I also want to leave the answer that on the board. I'll kind of go this. All right, so let's say I wanted to do it that way. Like I said, you don't have to write this down. This is not the way I would have done it. So I would have had to pull a sine x and attach it with the dx over there, giving me a sine to the 6th power. Now, sine to the 6th is okay to deal with, but it's more difficult than a sine squared. So when we have a sine to the 6th power, what we have to do is say, well, sine squared is 1 minus cosine squared. And then I have to raise both sides to the 3rd power. And a lot of people, when they do this, accidentally write cosine to the 6th power. That's not raised to the 3rd power. When I raise this to the 3rd power, it's 1 minus cosine squared raised to the 3rd power. I'd have to multiply it out. Okay. So now I can do my exchange. Sine to the 6th is 1 minus cosine squared, all raised to the 3rd power. And then I have a cosine to the 3rd power. And then a sine x dx for my du exchange. Now I can do my substitution. in for u. So I'm gonna get 1 minus u squared raised to the third power, u raised to the third power, and this is negative du. Put that. So the hard part of this is that you have a bigger polynomial to deal with and simplify before I can integrate. And that's why originally I chose the smaller one, so I didn't have to do as much simplification. I'm trying to think, let's try to simplify that. Let's take 1 minus u squared to the third power first. That is going to be 1 minus, well, let me think of this. All right. Yep. Trying to think if it's minus 3. Let me get the. Gotta get these signs right. Let me think just a moment. I'm gonna multiply that out. I get 1 u squared and 2. I think this is plus, and I think this is minus. All right. No, I should do the thing. I should just multiply it. I'm doubting myself, doubting my. One minus u squared. Have that right, have that. Knew something. Doubting myself. Here. There you go. Everybody see what I'm doing there? Just multiplying a polynomial out, and it took me longer than it should have, but that's what you end up with. Okay? Multiplying polynomials out. So. U to the third now can distribute also this minus sign, so we're gonna get minus 1 u to the third plus 3 u to the fifth minus 3 u to the seventh plus, that'd be 1 u to the ninth. All integrated with respect to u. That whole column is integrated with respect to u. Is that okay? Now we integrate that. It's just a standard polynomial, so negative 1/4 u to the fourth plus 3/6, which is the same thing as 1/2 u to the sixth minus 3/8 u to the eighth plus 1/10 u to the 10th plus c. Now we back substitute. And you end up with -1/4. U in this case was cosine, so that's cosine to the 4th. Plus 1/2 cosine to the 6th. Minus 3/8 cosine to the 8th. Plus 1/10 times cosine to the 10th. Plus some constant. Is that right? So there you go. And once you know, you get the exact same answer. Right? You might say, wait a second, that doesn't look like the same answer. But it turns out those two are the same answers. Those two are the same answers because if you apply this cosine squared plus sine squared substitution, let's say for sine in this one, you actually end up getting this kind of stuff. So remember, these substitutions aren't. When I apply a sine to the 10th power, what I'd have to do is take 1 minus cosine squared, raise that to the 5th power. So they are the same thing, but sometimes that's hard to see, obviously. So these are the same if you went through and applied this and raised, some things to the correct powers. But again, it takes quite a bit of polynomial multiplication to get there. Is that okay? So those are the same, even though they look a little bit different. Now, all of that is to say this polynomial multiplication, that can take a minute. And so the less of that I do, the better, right? So the less of this polynomial multiplication stuff I have to do, raise a polynomial, raise 1 minus cosine squared to the 3rd power, 1 minus u squared to the 3rd power. That. So that's why I chose, in my original, I chose to let my u be my sine, but I wouldn't have to do much. Okay, and so that's why I chose when you have two odd powers of sine and cosine, I chose the bigger, my u. All right. That's a lot of sines and cosines. So we can see that if we have an odd power on our sine or we have an odd power on our cosine, then this is doable, right? If we happen to have two even powers on both sines and cosines, then we actually have to use these double angle things. And that becomes more difficult. Okay. I don't ask you one of those on the homework, but if you did have two even powers, like sine to the 4th cosine squared, then you have to go sine squared equals 1/2 minus cosine of 2x. Cosine squared equals 1/2, 1 plus cosine of 2x. Multiply those things out. You might get a cosine squared again, and you might do another exchange. And you do that all the way down until you get to single powers of cosine and sine. And it might be cosine and sine of 8x. By the time you double the angle a few times. But if you had even powers, you'd have to do sine squares and cosines, those other 2 points. Okay. So instead of doing that, instead of spending a lot of time on even powers, at least right now, let's move on to the next connected pair of trig functions. The next connected pair of trig functions are secant and tangent. Because for one, their derivatives are connected. If you take a derivative of secant, you get secant times tangent. And if you take a derivative of tangent, you get secant squared. The other reason that they're connected is that if we take our Pythagorean identity, cosine squared plus sine squared equals 1, and divide both sides by cosine squared, you get an identity with secant and tangent in it. Cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared is tangent squared. And then 1 over cosine squared is secant squared. So secants and tangents are connected for those couple of reasons. The derivatives are connected. Derivative of secant is secant times tangent. Derivative of tangent is secant squared. And then that identity can be transformed into a secant tangent identity. The sine squared plus cosine squared equals 1 identity, can be transformed into secant to tangent. Now, this is going to work a little bit different. Okay, let's just do this first example. Secant to the third times tangent to the third integrated with respect to x. All right. So now here's what you do. So remember, the important part is what you peel off and attach with the dx. Okay, my 2 options, let's not write these down yet, but I'll talk through them. One option is to let my u be tangent. If I do that, when you take a derivative of tangent, you get secant squared. So I'd have to peel off the secant squared. And all the tangents could be gotten rid of. The other option is a secant. And when you take a derivative of secant, that is secant times tangent. So you're gonna have to peel off 1 copy of secant, 1 copy of tangent, and attach it to the dx. Okay. Which one of these do you think is gonna lead you to a better place? Peeling off a secant squared or peeling off a secant tangent? Remember, our trig identity that we're working with on any substitution is going to have squares, right? If I peeled off a secant squared, I'll be left with 1 copy of secant and 3 copies of tangent. That's odd powers. That's not very good. But if I peeled off a secant tangent, Now I have even power left over. So it turns out the one I want to do is I want to let my U be secant because I know I want to peel off a secant times a tangent along with my dx. That will leave me even powers with things.
At the end of our answer, should it be only one? I trick I didn't get. We can have multiple.
Trig function,
Or at the end of our problem, so like our answer. Let's see, like our answer for all of our other ones, we only have like one.
Oh, yeah. Yeah, one trig function, you're saying.
Mhm.
Yeah, so like it's always in cosines or always in terms of sines or, yeah, usually at the end, you'll always be in terms of one. Because in your back substitution, you'll just substitute in for u's.
Oh.
And there's gonna be no du's left, so. Yeah, so usually that's what happens. So that's the one I'm gonna do. All right, so let's peel off secant, a copy of secant. That'll be secant squared times tangent squared left over. And then that thing I underlined is my du exchange. Now, since my u is secant, I'm gonna get u squared, my tangent squared needs to be replaced. And I replace my tangent squared. Be careful about this, because this is a slightly different identity. A lot of people will do like 1 minus u squared because they're so used to sines and cosines. That's not the case with tangent and secant. With tangent and secant, tangent squared is equal to secant squared minus 1. Be careful about that. We're used to doing 1 minus sine squared, it's cosine squared, or vice versa. But with secants and tangents, order matters. All right, so I replace my tangent squared with a secant squared minus 1. And now I'm ready to substitute in for the u. So the whole thing about all of these is just prepping it to this point where now I can substitute for u. And I'll do some multiplication and integrate. When I integrate, I get 1/5 u to the 5th minus 1/3 u to the 3rd plus c. And now I just back substitute, like we usually do. U is secant, so 1/5 secant to the 5th power. Minus 1/3 secant to the 3rd power. Plus my constant. Does that work? So it's not like as straightforward as the sine cosine, because we're not dealing with just, oh, which one's even, which one's odd. It's like, what do you pull out? You can either pull out a secant tangent with the dx for the du replacement, or a secant squared for the dx du replacement. Does that make sense? Now, the other one on that page, I'll just write it down, we can go ahead and do it. Right now, that's secant squared tangent squared. So let's integrate secant squared times tangent squared with respect to x. This is one of those ones that you go, oh, this is a great one. Now, in the previous one, we took out a secant tangent. Obviously, if we took out one secant and one tangent, attached it to our dx, gonna leave odd, right? So that's a good indication that you want to try the other thing. Let u be tangent. And then the derivative of tangent is secant squared. And so secant squared of x times dx can be replaced with a du. And in this case, that's fantastic because we actually just have a secant squared that we can pull out. And attach to our dx. And once I do that, the remaining portion of the integration is tangent squared. And I don't have to do any fancy trig identity exchange here. I can simply say, now I can substitute and get a u squared times du. Since I didn't have a fancy trig identity input in there, that becomes 1/3 u to the 3rd plus a constant. And then I back substitute. One-third u is tangent, so that's tangent to the 3rd plus c. So that one's a really fairly compact one because I didn't have to use the trig identity or the secant tangent version of that Pythagorean identity. Any questions about that? Okay. So I kind of think of it again. By the time you get about right here, you should know if you chose the correct U and DU, right? And if you think a little bit ahead, sometimes you can see that coming. Say, well, my DU, I need to pull out, I need to have my secant squared attached to the DX. Or I need a secant tangent attached to the DX. So which one is gonna be more beneficial to me? And sometimes that's clearer than others. Just like if you had sine to an even power and cosine to an even power, there is a combination of even and odd secants and tangents that doesn't really work well. All right, where neither the pulling out a secant tangent will help, and pulling out a secant squared and attaching it to the x, that won't help either. So there is a version of that. And if you think through it, it's obviously not even, because we just did that one. It's not when they're both odd, because we just did that one. So it's when the troublesome is when secant is odd and tangent is even power. That's the troublesome one. That makes sense. By the way, if secant is even and tangent is odd, I can like make my u be my tangent, and that's just fine. Okay. But if secant is raised to an odd and tangent is raised to an even, that's weird. Can't do that one. Not through this method anyways. Not through this method. All right. So secant and tangents. Oh. Very simple. We'll skip one example. Well, if you can do secants and tangents, you can also do cosecants and cotangents. Because if we divided that Pythagorean identity by sine squared, it'd give us an identity in cotangents and cosecants, both raised to the second power. So cotangent squared plus 1 is equal to cosecant squared. And also the derivatives of cotangent and cosecant are linked in a very similar way to the way derivatives between secants and tangents are linked. Except when you take a derivative of cotangent, you get negative cosecant squared. And when you take a derivative of cosecant, you get negative cosecant times cotangent. Remember that? Standard derivatives there. Is that okay? Let me write that down on the board real quick. I'm not gonna do an example because it's so similar to the secant tangent thing that we just did. But I do want you to have this in your notes. If using cotangent and cosecant substitutions. If I let my u be cotangent, my derivative with respect to x of cotangent is negative cosecant squared. So remember, tangent gave you secant squared, but it was a positive secant squared. Cotangent, when you take the derivative, gives you cosecant squared, that's negative. And if you let your u be cosecant of x, then doing this exchange gives you negative cosecant times cotangent. And then the Pythagorean identity becomes cotangent squared plus 1 equals cosecant squared. Okay? So it's that, and that is very, very similar to our tangent and secant exchanges. So I'm not gonna do one of those just because you just have to throw in a negative sign if your dx du exchange. Other than that, it's exactly the same. Now, the last thing I want to do as far as substitutions in trig functions go, everything so far we've dealt with like cosine of x, sine of x. And even if we were dealing with cosine of 30x and sine of 30x, since the arguments inside of sine and cosine would have been the same, we could have still dealt with that in the same fashion. But what happens when we don't have the same arguments inside of cosine or inside of sine? What if we have something like cosine of 3x times cosine of 7x? And we want to integrate that. So I have different things on the inside. Well, it turns out what we're going to use is some trig identities that you may or may not have seen back when you looked at trig stuff, and probably what would that been? Pre-calc, imagine. Pre-calc days. Looking at trig stuff. So we do this. If you have sine of an argument times sine of another argument, it's 1/2 times the quantity cosine a minus b minus cosine a plus b. A and b are the different arguments. Sine of a times cosine of b is equal to 1/2 sine of a minus b plus sine of a plus b. Cosine of a times cosine of b equals 1/2 cosine a minus b plus cosine a plus b. Now, these are not things that you should commit to memory, okay? Have them written down in your notes or have a big trig substitution sheet handy that you can look at or print this out or whatever. These are not things you need to commit to memory. I would say that Pythagorean identity, cosine squared plus sine squared equals 1. That's probably one that everybody should know. But these are more specialized. So now let's apply this identity to what we just went over. Or what we just asked. If I have cosine of 3x times cosine of 7x, and I want to integrate that with respect to x, what am I gonna do? Well, I simply look back to that identity and say, oh, this is cosine times cosine. That's the third option. So I'm going to replace cosine of 3x times cosine of 7x with 1/2 times the quantity cosine A minus B. Now, A minus B would be 3x minus 7x in our case. Plus cosine of A plus B. In our case, that would be 3x plus 7x. So cosine of A minus B plus cosine of A plus B, all multiplied by half. Then, hopefully this is not too much. I'm gonna do two things at once. I'm gonna say this 1/2 is distributed to both cosines. So it's 1/2 cosine of negative 4x plus 1/2 cosine 10x integrated with respect to x. Is that all right? The antiderivative of cosine is sine, and because our arguments are not just x, we have to divide, but they're linear, we have to divide by the -4 in this case and the 10 in this case. Right? Works like an exponential function, you divide by the coefficient here. So when I divide by -4, I get 1/-8. Sine -4x. Plus, when I divide by 10, 1/2 divided by 10 is 1/20. Sine 10x. Then plus it. Is that okay? So I simply apply that rule. And then do my understanding of how to integrate cosine of coefficient times x. Everybody okay with that integration, coefficient times x? Does that throw you off? It's the same thing as when you have e to the ax. And what you do with that one is you take 1/a e to the ax plus c, right? Well, if you have integrate sine of ax, normally the integration of sine would be a negative cosine. So you do the negative cosine piece, but since it's ax, you divide by it. And the same thing with cosine. Normally, the integration of cosine would be a positive sign. If I have cosine of AX, it is the positive sine of AX. And then I divide by A. So all three of those are basically the same kind of concept. We okay with that? I've done that twice now in class, or at least twice, maybe 3 or 4 times, I don't know. But might as well write it down. By the way, if somebody told you, actually, they got a positive 1/8 times sine of positive 4x plus 1/20 times sine of 10x plus c, these two are the same thing. Right? Sine is an odd function, so the negative, you could be brought outside, multiplied. And by the way, cosine is an even function, so cosine of negative 4x is the same thing as cosine of positive 4x. So these two are the same. You can write either way in Moodle, so it's not. Moodle should recognize those are the same. All right. Let's do one more of that type. So I'll write this down on the board. And then I'll flip back to the trig identities that we're gonna need. This time sine of 8x multiplied times cosine of 4x. I want you to take just a minute and use one of those exchanges. To solve that problem. All right. Now, I want to say something about these trig identities here that you see on this screen. You'll notice that the first and third both have two sines or two cosines. So if you end up with a problem with two sines or two cosines, and you kind of swap the order of A and B, it's not going to be that big of a deal. All right. Because multiplication is commutative, cosine of A times cosine of B is the same thing as cosine of B times cosine of A. Okay, so if you swap which one you call the A and which one you call the B, not a big deal in the last problem. So in the last problem, if I said, well, let's use 7x for my A and 3x for my B, I would have ended up with the exact same answer. Instead of 3x for my A and 7x for my B. However, in this one, the order does matter. The A is the one that's the argument inside of sine, and the B is the one that's like inside the cosine argument. So just be very careful on that one. You don't have to be as careful on the other two, which one you call the A, which one you call the B. Here, the A has to be inside of the sine. The B has to be the one inside the cosine. So when I do 1/2 sine of A minus B, I have to be really careful that I use the A as 8x and the B is 4x. On this one, that's not most people wouldn't throw that off or get thrown off by that. But sometimes if the smaller coefficient is here, people want to subtract naturally the bigger minus the smaller. But make sure you do that correctly. That's all I'm saying. And then sine of, well, when we add these two, you get 8x plus 4x. So this is the one where it really needs to be A minus B, no matter which coefficient is bigger. And the A needs to be the one inside of sine. So with that being said, we get 1/2 sine of positive 4x plus 1/2 sine of 12x, all integrated with respect to x. We utilize what we just utilized. Antiderivative of sine is negative cosine. So negative 1/8 cosine of 4x minus 1/24 cosine of 12x plus c. Right. And so that's basically all of 6.3. 6.3 is essentially utilizing trig identities. Here we utilize the trig identities basically directly to make our integration doable. And then in the other case, we utilize the U substitution along with trig identities to make our integration doable. Okay. Now there's lots and lots of other trig identities that you could use. I touched on some of those, but for any ones that I'm going to ask you, it's basically this trig identity along with different versions, whether it's the cotangent, cosecant version, or the secant tangent version, or the sine cosine version of that Pythagorean identity, right? Cosine squared plus sine squared equals 1. Does that work? So some sort of derivation of that. Any questions? All right, well, that's it for class 11:20. So we will stop there and I will see you all next time.